In continuation with the sequence similarity alignment and algorithm, here we discussed about your various sequence amino acids and nucleic acid comparison, the details. Now we are going to see how we are going to compare the two sequences. Here point mutations are available, and another example indel, which was difficult and very indel mutations are difficult to align the sequences. Point mutations where we can see the nucleotide change that are given in bold letters, whereas indel means insertion or deletion mutation. Here we can see that how this is arranged, and further it contains your mutations, point mutations and gaps are there. Since there is no nucleotides in this question, they are deleted, we call them as gap. How to score such sequence? So if the nucleotides from two sequences are matching, they are similar, means we are giving +1 value. If they are not similar, it is totally different, we give the score of 0. And gap penalty, if there is a gap present in it, we give the gap penalty of -1. Here we can see there are 18 such matches are found in the case of this. So 18 into +1, and there are two mismatches that is given in the bold letter A and T, A and C, and nearly 7 gaps are available, 7 into -1. So 18 plus 2 into 0, 0 plus 7 into -1, -7. So 18 minus 7, the score is +11. We want to find alignments that are evolutionarily likely to be present, which are close to each other, and most possible alignments we want to give. If more gaps are available, we can achieve this penalizing more for a few gaps than for extending in the existing gap. So here is scoring sequence alignment for another one. If there is gap found in the several places, we are giving the origination score also by -2 value. Okay, like mismatch score, here we are providing the origination of the gap with -2 value. So here we can see the comparison, match and mismatch score +1, mismatch score is 0, origination and length penalty. Origination is -2 if the gap is present the origination, and gap penalty is -1. So automatically match is 18 into 1, mismatch is 2, that is A and T, A and C. They are mismatching, they are given in bold letters. Origination, there are two places where we have the gaps are available, so 2 into -2, and length is 7 gaps are found, so 7 into -1, -7. So 18 plus 2 into 0, 0 plus 2 into -2, -4, and 7 into -1, -7. -7 plus -7 and -4 becomes -11. So 18 minus 11, the score is 7 in this case. Scoring similarity, we can only score aligned sequences. DNA is scored as identical or not. Modifying and scoring gaps, single or multiple base gaps are taken into consideration. Same manner in the case of the amino acids also, varying degrees of similarities are noted. And further in the case of the amino acids, the number of mutation for conversion to one amino acid to the other amino acid are also taken into consideration. If one amino acid is replaced with the same amino acid, that is due to degeneracy of the genetic code in the third nucleotide position, so that is not taken into much consideration. If identical amino acids are substituted, for example, if one hydrophilic amino acid is substituted by another one, or one hydroxy amino acid like serine is replaced by threonine, or alanine by valine, or aspartic acid by glutamic acid, or a basic amino acid by another basic amino acid, histidine by arginine, or aromatic amino acids like phenylalanine can be replaced by um, tyrosine or tryptophan, etc. So we call that as chemical similarity. And number of observed mutation frequency, how many times the particular amino acid is conserved, or how many a particular amino acid is keep on changing, that is also taken into consideration. The PAM matrix is calculated from the observed mutation in the protein family. So DNA scoring matrices are, there are three different types of DNA scoring matrices. Basic matrices are available. One is identity matrix, another one is blast matrix, and the third one is transition transversion matrix. Identity means whether it is similar or not. So if sequence A matches with B or not. So if the nucleotides present, the A is matching with the B, we consider that as identity. So for example, we can see one sequence is written in the top, another in the left side, ATGCG and ATCG. Here the matrix we can see A and A in the first column, A of I comma J, we call it as a 1 of 1. A is equal to 1, so we are given 1. A when compared with T, it is 0, and the rest of the things are 0. The second row we come across A, T doesn't matches with A, so it is 0. And second row and second column, T matches with T, so 1. The next is 0. Same manner, the third column, C with C is alone matching, so it is given 1 score. And last column, G with matches with G, rest of them are 0. Whereas in the case of the blast matrix, the score is totally different. The matching scores are given a 5 and mismatching scores are given -4. So simply we can replace 1 with 5 and 0 by -4. Whereas in transition transversion mutation, totally different. Transition means purine by purine, that is when adenine is replaced by guanine, that is purine by purine. If cytosine is replaced by thymine, that is pyrimidine by pyrimidine, we call it as transition mutation. Whereas in transversion means a purine by pyrimidine, adenine may be replaced by cytosine or thymine, or guanine by cytosine by thymine, or vice versa. So when adenine is matching, A and A is matching, we are giving 1. When purine by pyrimidine, we are giving -5. And purine by another purine, we are giving -1 in this case. If they are matching, exact nucleotides are present, we are giving value of 1. And if it is by transversion, we are giving -5, that is purine by a pyrimidine -5. A purine by another purine, we are giving -1, or vice versa. So here we can see the difference between the DNA scoring matrix. This question will come in your part A or part B or part C. Same manner in the case of the amino acids too, we come across PAM matrix or point accepted mutation matrix. A single amino acid change is taken into consideration, but in the case of the amino acid, we seek for the chemical similarity on replacement during mutation, already I told you, or how many times the particular amino acid occurs. So we provide the score for it. So it was developed by the lady called as Day of during the year 1920. So it is also known as Day of matrix. So PAM matrix is a matrix. It is a multiplication. PAM is PAM1 into PAM2 into PAM3. Likewise, 250 times we are multiplying it and we are getting it. So how to find the optimal alignment? To find the optimal alignment computationally, it is very hard. How many gaps are there? How many possibilities are there? So we make use of a dynamic programming concept for this optimal alignment. We make use of two algorithms. One is a Needleman-Wunsch algorithm, and the one is Smith-Waterman algorithm. First one we are going to see. So this is optimal alignment where we have match is 1, match score is 1, mismatch is 0, and gap is 1. let us write the programming concept table. So we are writing, though in the first sequence we have only 5 nucleotides and second sequence we have 7 nucleotides. In the Needleman-Wunsch algorithm step we are writing first row and column with number of nucleotides by penalty that is -1, 2, 3, -4, 5, and here -1, 2, 3, 4, 5, 6, 7. If they are matching, that is A is matching with A, so we are providing 1. If it is mismatching, the second, that is A is mismatching with C, means we are providing 0. So horizontally as well as vertically we move by providing the gap penalty, and diagonal move also we are providing where the score is match and mismatch score is provided. So horizontal vertical move provides the gap penalty, whereas diagonal move provides the match and mismatch score. So we are taking the maximum 3 possibilities. Here we can see that. So first one, the second one, A doesn't matches with C, so we are providing 0. Then further we are providing the gap penalty of -1, 2, 3, like that. The second column, same manner we fill out the rest of it. We see that C is matching with C, so we are providing 2. And rest of them it is 1, 0, -1. The third column, third row, it is -1, then 1 and 2 and 1, 0. Likewise keep on adding. So we keep on going and we get optimal score of alignment is calculated at the lowest right corner. From that we are moving. So we go diagonally to reach the 0. When we reach it, automatically the up arrow shows the gap in the top sequence and left arrow gap in the left sequence, and diagonal arrow represents the aligning of both the position. The one path from the previous table. So the score corresponding alignment for this is +2. This is how the system calculates by using a Needleman-Wunsch algorithm. And there are some semi-global alignments are available, which is shown in the table. Here we can come across another example for semi-global alignment. So we are initializing first row and column to all zeros, and we are allowing the free horizontal and vertical move in last row and column, and diagonal line represents the value and we get it. Local alignment. Global alignment score the entire alignment, whereas semi-global alignment allows the unscored gaps, and local alignment provides the best matching, that is alternate. That is following a type of algorithm, what you call it as Smith-Water algorithm. Here we are giving mismatch is -1 in this case. So all the mismatches, here the scores are given as 0, and the maximum, from the maximum value we are going diagonally, and this is a problem, this is given for you. That's all about your 2 types of algorithm, Smith-Waterman algorithm and Needle-Wunsch algorithm. One is used for global alignment, another one is for local alignment, that is used to calculate the matching and mismatching of sequences between 2 persons or species or 2 different species by the system or by the bioinformatics, so that the entire length of the nucleotide, whatever may be the number of nucleotide, may be in millions or trillions, whatever it is, that can be easily calculated. and that information can be stored very easily by the system. Thank you.